Have you ever really stopped to think about something as simple as, say, measuring a teaspoon of salt?
Yeah.
Or why that bottle of antifreeze you pour into your car works in both freezing cold and blistering heat?
It's funny you mention that because underneath those everyday actions is this incredibly precise world of quantitative chemistry. And that's really what we're diving into today, the heart of analytical chemistry.
Right. It's about figuring out what something is made of. That's the qualitative part. But more importantly for us, exactly how much of each thing is in there, the quantitative part.
Exactly.
So that's our mission for this deep dive. We're going to map out the foundational tools that let chemists and engineers measure the world with, well, with life-saving accuracy sometimes.
We'll start with the language, how we talk about concentration. Then we'll get into the actual tools and the obsession with precision in the lab.
And finally, we'll see how it all connects to things like keeping roads safe in a snowstorm. So we're looking at three big areas, the language, the tools, and then the real-world applications.
That's the plan.
Okay, so let's start with that language, the language of concentration. If I want to say how much salt is in a glass of water, it turns out there isn't just one way to say it. There are three main ways, and the differences are subtle, but really important.
They are. And the key difference is always the denominator. It's what you're dividing by. The most common one you'll see is molarity, with a capital M.
Molarity. That's moles of the solute per liter of the solution, right? The whole thing.
The whole thing, yes. If you're in a lab using a volumetric flask, molarity is your go-to. It's practical.
But I read that molarity has a kind of a hidden weakness because volume changes with temperature.
It does. It's a huge drawback. If you make a 1 molar solution in a cold lab and then take it into a hot room, the volume expands and poof, your molarity has actually changed.
So it's not fundamentally stable.
Exactly. And that's a problem for studying basic properties, which is why we have molality,
Right.
with a lowercase m, that's moles of solute per kilogram of solvent.
So you're using mass, not volume.
Right. And since mass doesn't change with temperature, molality is rock solid. It's the unit we always use for colligative properties, which we'll definitely get to later.
Okay, and that brings us to the third one, the one that always felt a bit confusing to me, normality, capital N. This one is based on, what, equivalence?
Yeah, and that's where the confusion comes in. An equivalent is based on something called equivalent weight. You take the molecular weight and divide it by the number of reacting units. Think of it as the molecule's reaction power.
So the power of the molecule can change.
It can, and that's the tricky part. A substance's equivalent weight, and therefore its normality, depends entirely on the specific chemical reaction it's in.
That sounds dangerous. I mean, if I'm a lab tech and I grab a bottle of phosphoric acid, how do I know which normality to use?
You've hit on precisely why it's used less and less. Phosphoric acid, Tex3, Tex-PO44, has 3 hydrogens it can give away. Depending on the reaction conditions, maybe which indicator you use, it might only give up 1, or 2, or all 3.
So its equivalent weight could be its molecular weight divided by 1, 2, or 3.
Exactly. So its normality changes depending on what you're doing with it, even though its molarity is constant.
It seems like it was trying to be a shortcut for calculations, but ended up being too ambiguous.
It was. For certain things, like redox reactions, where it's all about electron transfer, it's very useful. The formula is simple. Tex N, or is a number of electrons. But because N can change, it just became too context-dependent for general use.
Which brings us to the next point. If your language needs to be that precise, your tools have to be even better. The whole quest for accuracy.
And the stakes are just immense. The classic tragic example is the NASA Mars Climate Orbiter. A multi-million-dollar mission lost because one engineering team used English units and another used metric units.
A simple unit conversion error.
A fatal one. And if that can happen on that scale, you can imagine how critical a fraction of a milliliter is in a medical lab.
So let's talk about the tools for measuring volume. They are not all created equal. Not by a long shot.
Not at all. You start with something like a graduated cylinder. It's fast, it's easy, but it's really just for approximations. A 100 milliliter cylinder might be off by a full milliliter. That's a 1% error.
Unacceptable for real analytical work. So then you upgrade.
You upgrade to something like a volumetric pipette, a transfer pipette. A 10 milliliter one of those will deliver 10.00 milliliters, plus or minus maybe 0.02.
Wow, okay. Like a 50-fold jump in accuracy.
It's a huge jump. Same with a volumetric flask, which is designed to contain a single perfect volume. And using them correctly is a whole skill in itself.
Right. Reading the bottom of the meniscus, avoiding parallax error by keeping your eye level.
All of it. We even calibrate them by weighing a volume of pure water. And that rigor extends to how we write down the numbers. Two significant figures.
Or SF, yeah. They're so important because they don't just tell you the number, they tell you the uncertainty in the number.
Precisely. You write all the digits you know for sure, plus one estimated digit.
I saw a really interesting rule in our notes about logarithms, like when you're measuring text speed.
Yes. With a log value, only the digits after the decimal point are significant. So if you get a text P of, say, $2.45, that's two significant figures, the 4 and the 5.
Why is that?
Because the 2 just tells you the power of 10. It sets the scale. The actual measured precision is in the numbers that come after.
Got it. Okay, and the last piece of this precision puzzle is mass. Making sure what you weigh is actually what you think it is, which means drying.
Oh, absolutely. You use an analytical balance that can measure down to a 10,000th of a gram. You dry your sample in an oven to get rid of water, but then comes the most critical step.
The cooling. You can't just leave it on the bench.
Never, because a perfectly dry sample is like a sponge for atmospheric moisture. It'll suck water out of the air in seconds and ruin all your careful work.
So you had to put it in a desiccator?
You have to. It's a sealed container with a drying agent, like silica gel, that keeps the air inside perfectly dry while your sample cools. It's a simple tool, but without it, all that precision is lost.
So all this incredible effort just to get one reliable number. Let's apply that now to the workhorse of quantitative chemistry. Titration.
Titration, right. This is where you use a solution of a known concentration, the standard, to find the concentration of an unknown, the analyte.
But there's a key distinction we have to make here between the equivalence point and the end point.
A crucial distinction. The equivalence point is the theoretical moment when the reaction is perfectly stoichiometrically complete. It's a mathematical ideal.
And the end point is what you actually see in the lab.
Exactly. It's the physical change, usually an indicator changing color. And the tiny difference in volume between when the color changed, Vtex, and when the reaction was actually done, Vtex S, is your titration error.
So good chemistry is minimizing that error.
Yes. And you can do some amazing things with the right indicators. For example, you can analyze a mixture of two bases, like sodium hydroxide and sodium carbonate, in one go.
How does that even work?
You do it in 2 steps. First, you add an indicator like phenolphthalein. You add acid until it turns colorless. At that point, you've neutralized all the strong base, the hydroxide.
Only half the carbonate, right?
Exactly, only half. It turns it into bicarbonate. Then you add a different indicator like methyl orange to the same flask.
And you just keep going.
You keep adding acid. The second volume of acid you add neutralizes that remaining bicarbonate. By comparing the first volume to the second, you can calculate the original amounts of both. It's brilliant.
That is really elegant. It's like a chemical magic trick based on picking the right tool. Okay, so from measuring volume and titration, let's switch to measuring mass with gravimetric analysis.
Right. Here, the idea is to convert your analyte into a solid, a precipitate that you can filter, dry, and weigh.
But for that to work, the precipitate has to be, well, ideal. What does that mean?
It means a few things. It has to be easy to filter, have very low solubility so you don't lose any, be stable and not react with the air, and you have to know its exact chemical formula after you dry it.
The filtering part sounds like the biggest challenge, getting the particles big enough.
It is everything. You have 2 extremes. You can get a colloidal suspension, which is just these tiny, tiny particles that float around and go straight through your filter. That's a disaster.
Or you get a crystalline suspension.
Right. Big, beautiful crystals that settle right to the bottom and are easy to filter. The goal is always to get the crystalline solid.
So how do you do that? How do you control it?
You control the rate of reaction. The technique is called homogeneous precipitation. Instead of just dumping your precipitating agent in all at once, which creates a huge concentration spike and forms a colloidal mess.
You generate it slowly inside the solution itself.
Exactly. For instance, you can use urea. When you heat it in water, it slowly decomposes and generates hydroxide ions. Slowly, evenly, everywhere at once.
So you never get those localized high concentrations.
You don't. And the result is dramatic. If you precipitate aluminum hydroxide by just dumping in a base, you get this goopy, gelatinous mess. If you do it homogeneously with urea, you get a dense, pure, beautiful solid. That's a dream to filter.
Wow. So the how is more important than the what. Okay, let's step outside the lab now and look at how these ideas show up in the real world, starting with colligative properties.
This is such a cool concept. The aha moment is that these properties don't care about the identity of what's dissolved, just the number of particles.
Like freezing point depression and boiling point elevation.
The two big ones. And the classic example of freezing point depression is putting salt on icy roads. The salt dissolves and the particles, the ions, get in the way of the water molecules trying to form an ice crystal lattice.
So it lowers the temperature at which water can freeze.
It does. And salt is super effective because it's an electrolyte. One little textile unit breaks apart into two particles, a sodium ion and a chloride ion. It gives you double the bang for your buck compared to something like sugar.
Which our sources say makes it about 6 times more effective.
Roughly, yes. And we see this same idea, but in a more advanced way, in car coolant with ethylene glycol.
Right, because it does 2 things at once.
A chemical 2-for-1, like you said at the start. It depresses the freezing point so your engine blocks don't crack in the winter, and it also elevates the boiling point so your radiator doesn't boil over in summer traffic.
It's the ultimate temperature bodyguard for your engine. Okay, I have to ask, let's debunk the kitchen myth. Adding salt to pasta water to make it boil faster. I do this. Am I wasting my time?
You're in good company, but... Yes, chemically you are. It's a great tradition for flavor, but the science doesn't back up the speed claim.
So it does raise the boiling point, right?
It does. That's the colligative property.
Yeah.
But the amount of salt you add to a pot of water might only raise the boiling point by maybe 0.2 of a degree Celsius.
That's it. 0.2 degrees.
That's it. So the idea that your pasta is cooking significantly faster at 100.2 degrees versus 100 is, well, it's just not true. It's ridiculous. Cook pasta as you please.
Okay, lesson learned. Finally, let's look at a global application of this. Reverse osmosis, or RO.
RO is massive. It's how we get fresh water from the ocean. Osmosis is the natural tendency for water to move across a membrane from a less concentrated solution to a more concentrated one.
To try and dilute it.
Exactly. In reverse osmosis, we apply huge amounts of external pressure to fight that natural tendency and literally force the pure water molecules through the membrane, leaving the salt and impurities behind.
You're reversing a natural colligative process to purify water. That's incredible. Okay, let's bring it all home with one last mechanism of control. Buffers and pH.
Right. We know the pH scale is a measure of acidity based on water's ion product constant, Ka $, which is $1 times 1014. And buffers are the key to controlling pH.
They're solutions that resist changes in pH.
They do. They're usually a weak acid and it's salt, and they are absolutely fundamental to life. Our blood has to be buffered at a pH of about 7.4. If it deviates even a little, we're in big trouble.
So how does that resistance actually work? What's the mechanism?
Let's use the acetic acid sodium acetate buffer. If you add a strong acid, the Textia plus, it gets neutralized by the acetate ion, the conjugate base. If you add a strong base, the Texpro away, it gets neutralized by the acetic acid molecule itself.
So it's like a chemical sponge. It has something ready to absorb either kind of attack.
That's a perfect way to put it. And to calculate the pH of these sponges, we use the Henderson-Hasselbalch equation.
Ah, yes, the famous equation.
Yeah.
Plus log of the salt concentration over the acid concentration.
And what that equation shows you is that the pH is controlled by the ratio of the salt to the acid. As long as that ratio stays pretty stable, the pH stays stable. It's used everywhere from medicine to environmental science.
So we've really gone from measuring a pinch of salt to purifying oceans and stabilizing our own blood. We covered the language of concentration, the high-precision tools of the lab, and these huge macroscopic consequences.
It all connects. The accuracy you learn with a pipette is what allows you to understand and engineer a system as complex as a biological buffer. That depth of understanding is what analytical chemistry gives us.
Which leads us to our final thought for you to take away. We know from that equation that a buffer works best. It has its maximum buffer capacity when the ratio of salt to acid is 1:1.
Right, which is when the pH of the solution is exactly equal to the pKa of the weak acid.
But here's the really elegant part. The pH of a buffer is also almost completely independent of dilution. You can add water, and as long as the concentrations don't become tiny, the pH barely budges.
So think about this. Why is designing a system that simultaneously resists attack from acids and bases, has its maximum power when text, and is robust against dilution? Why is that one of the most powerful and elegant examples of chemical engineering you can find? You now have the tools to really dive into that question yourself.